Hello again, and I'm going to do a podcast on fractional derivatives. So hopefully you'll enjoy this. Um, yeah, you might ask, what are fractional derivatives used for? And they're used in physics to model phenomena that requires memory. It's also mathematical curiosity uh, in its own right. You may ask, can you develop the fractional differential geometry using fractional derivatives? And that's actually not as easy as it sounds. So hopefully I'll be able to show you why. Um, yes. So my main motivation for fractional derivatives is so perhaps it can be used to build new physics. If you recall the Dirac equation, the Dirac equation is formulated by taking the square root of the Laplacian, uh, and that requires the use of a Clifford algebra, right? So the question is, what if you would take the fourth root of a Laplacian and then try to formulate an electromagnetic theory using the fractional derivatives? Perhaps you can conjecture the existence of a spin 1/4 particle instead of a spin 1/2 particle. But however, this is all speculation and ideas. So that's my main motivation for fractional derivatives. It's the construction of a fractional differential geometry and possibly the exploration of new physics by building new mathematics. Um, yes, so anyhow, let's do the basics. Let's recall what the derivative operator in one dimension is, right? So hopefully this is going to work. The derivative operator takes a differential function on the real line, right? And gives me a function on the real line. That doesn't necessarily need to be continuous, it just needs to be a function. An example of a function that has a derivative everywhere is the Weierstrass function, right? But when you take the derivative, it's not continuous everywhere. So almost everywhere, except on the measure zero, right? So yeah, so ignoring the details of measure theory, right? The derivative operator has this property that it takes a polynomial x to the n, right? And it gives me a polynomial of lower degree, x to the n minus 1. Okay, right, so, excuse me. Let's put this here. Yes. So now we want to formulate, right, an operator which we're going to call, yes, so I made a mistake here, so I need to learn to spell. Dx to the 1/2 is going to be the square root of the derivative operator, right? Such that when you apply that operator to itself, then you get the derivative operator, right? And the approach that we're going to use is detailed in the following reference, which I'm going to show in about a minute, or pretty soon, I'm sorry. Hi, so this is the reference that I was telling you about. Um, it's a paper that I found online. It was published in the Sigma Mathematics Journal. It's a survey of how many fractional derivatives are there. If you do a Google search on these authors by Duarte Valerio, Manuel Ortiguera, and Antonio Lopez, you should be able to download it for free. And the paper is very thorough. It starts with the Laplace transform and it formulates a possible definition using the Laplace transform or Fourier transform, I guess. But that's not enough for our purposes, but it also points out that fractional derivatives do not obey the Leibniz rule, which is the rule of a derivation, but they obey the generalized Leibniz rule, something that will create problems in differential geometry. So this is what, because in differential geometry, a vector field is a derivation, and derivations have to obey the Leibniz rule. So other than that, the definition that we're going to formulate is essentially this one right here, that is with theta equals 0. Um, so yeah, so if you're interested in learning more about fractional derivatives, I recommend you read this paper. So I'll try to make it available online too as well. Thanks. Okay. Now, so essentially what we're going to do is we're going to rewrite the derivative as a limit, right? So f prime of x is equal to the limit as h goes to 0 of f of x minus f of x minus h divided by h, right? That's well known from calculus, right? Another trick that we know from quantum mechanics is that if we apply the momentum operator, right, onto, well, something that looks like the momentum operator onto a wave function, right? In this case, this is something that looks like a momentum operator because there's no IH bar in it, right? It's just H and a derivative operator, right? And we apply it to a function, right? F of x. Let's do the details, right? So the definition of the exponential is the sum n equals 0 to infinity of h to the n, and then the derivative operator itself applied n times, divided by n factorial. This whole thing is acting on f of x, right? And if we write this out explicitly, as it acts on each of its terms, the left-hand side acts on the right-hand side. That is, this side acts on this side. Then I get the following sum, right, to infinity, h to the n, the nth derivative of f at, well, evaluated at x divided by n factorial. Now, let's see what happens when, if I rewrite this as, I'm sorry, apologies, x plus h minus x to the n, f of n of x divided by n factorial. And when I rewrite that as that, then this turns out to be f of x plus h, right? So this is an algebraic trick from functional operator theory, I guess, right? So if I take the exponential map of the derivative operator, right, and act on a test function, then that amounts to the shift in the argument of the test function, basically. Now, I can do the same thing with minus h, right? So if I do the following, minus h ddx, e to the minus h ddx, acting on f of x, then this is equal to f of x minus h. Now that we know that, we can rewrite the definition of the derivative, right, operator as the limit as h goes to 0 of f of x minus f of x minus h divided by h. And we can write this as a difference of operators, functional operators, that is, right? The identity operator minus e to the minus h ddx, right? Acting on, divided by h, acting on f of x. Now, this term right here, it's an operator itself, right? And we can take care of its square root using the binomial theorem. Recall the binomial theorem, right? So that 1 plus x to the alpha is equal to the sum n equals 0 to infinity alpha n x to the n, right? For this right here is the generalized binomial coefficient, right? Okay, so we're going to use alpha equals 1/2 in this case, right? If we do that, then 1 minus e to the minus h ddx to the 1/2 is going to be equal to the sum n equals 0 to infinity of 1/2 n, right? So this is a generalized binomial coefficient of minus e to the minus h d dx to the n. So this turns out to be equal to the sum n equals 0 to infinity minus 1/2 n minus 1 to the n e to the minus nh ddx, basically. So that is the definition of that operator. And now we can formalize our definition of the fractional derivative, right? So ddx to the 1/2 f of x is going to be equal to the limit as h goes to 0, 1 over h to the 1/2, and then this infinite sum right here. N equals 0 to infinity, minus 1/2 n, minus 1 to the n, and e to the minus nh ddx, acting on f of x, basically. Now, I'm going to write down that without the operator formulation or notation, right? So this is equal to limit as h goes to 0, 1 over h to the 1/2, sum h equals 0 to infinity of minus 1/2 n minus 1 to the n f of x minus nh. So basically, this is our definition of the square root of the derivative operator, which is the first attempt at defining a fractional derivative, right? Notice that this definition is different than the ones that you'll find online using integrals. Those were the original definitions that were formulated back in the 1800s, or I don't know, in the past actually. This is a newer definition, and the reference that I showed you earlier has more details on it. It has more of a history actually. Okay, so now that we know this definition, or we've formulated a definition for the fractional derivative, in the square root of the derivative operator, right? Now we can do some examples. So let's do an example. First example is the easiest example, right? Let's suppose f of x is equal e to the x, right? So now if we do that, then the fractional derivative of f of x, right, it's going to be equal to the sum h goes to 0 to infinity, 1 over h to the 1/2, the sum n equals 0 to infinity of minus 1/2 n minus 1 to the n, and then this is going to be e to the x minus nh, right? And the nice thing about this formulation is that this e to the x can be factor out. So that's what we're going to do, right? So this is equal to e to the x, the sum h n goes to 0 to infinity. But I'm making some mistakes here in my writing, so I should be careful. Yep. 1 over h to the 1/2. I am sorry. I am going on autopilot and I'm doing things incorrectly, so this should be the limit as h goes to 0. This is the limit as h goes to 0. The sum n equals 0 to infinity, minus 1/2 n, minus 1 to the n, e to the minus nh, right? Now, if I calculate this correctly, right, then this is equal to minus 1 e to the minus h to the n, right? So this thing this whole expression right here is nothing else but using the binomial theorem in reverse, 1 minus e to the minus h to the 1/2, basically, right? Which is the same thing as e to the x, the limit as h goes to 0 of 1 minus e to the minus h divided by h, everything to the 1/2, by continuity of the limit, right? Now this expression inside, right, is nothing more than 1 basically. So this is equal to e to the x. So we've shown that the square root derivative of e to the x is itself, which is nice. It's something that holds with the regular fractional derivative operator, right? Well, let's do the next example, which is the next challenge, which is going to be, well, let's see what happens when we consider e to the ax equals f of x, right? Will we still get the same answer? Okay, so we'll do the same calculation, right? So the square root derivative of e to the ax is equal to, okay, here we go. It's going to be equal to the limit as h goes to 0 of 1 over h to the 1/2 of this infinite sum n equals 0 to infinity minus 1/2 n minus 1 to the n, and then this is going to be equal to the e to the ax minus nh, right? And once again, what we're seeing here is that we can pull out this term from the sum and the limit because it's independent of h and n, right? So if we do that, then we get e to the ax, and then we get the limit as h goes to 0, 1 over h to the 1/2, the sum n equals 0 to infinity, and then in this case we get minus 1/2 n, right? Minus 1 to the n, e to the minus a and h, right? Now this term right here is the same thing as e to the minus a h to the n, right? Now, if I want to do the same trick as the one before, then I better multiply top and bottom by a to the 1/2, right? Because and then I can pull out the a to the 1/2, so I get a to the 1/2 e to the ax, and I get the following expression for the limit, right? The limit as h goes to 0, 1 over ah to the 1/2, right? The limit as from n equals 0 to infinity minus 1/2 n minus e to the minus h to the n, right? Now this term right here, if we do the binomial theorem in reverse, then we get back the following condition, right? I guess e to the ax, the limit as h goes to 0, 1 over ah to the 1/2. This is going to be nothing more than 1 minus e to the minus ah to the 1/2, basically. Now I can do the continuity of the limit and pull out the square root sign, so I get a to the 1/2 e to the x a, right? The square root of the limit as h goes to 0, 1 minus e to the, apologies for that, so e to the ah divided by ah, right? Now this term inside of here, right, this goes to 1 as h goes to 0. If I didn't have the ah in the denominator, it will go to a instead. So, but since I put it there, then it just goes to 1. So this whole expression goes to e to the a to the 1/2 e to the ax. So the fractional derivative, or the square root derivative of e to the ax, is a to the 1/2 times e to the ax, right? So now we have a realization, right? So let's say what happens when a is equal to -1, right? Then the square root derivative of e to the minus x, right, is going to be equal to square root of -1, which is I, or plus or minus I, whichever it is. I don't know, it's a square root of -1. Don't know which one it is, but it's plus or minus I, e to the minus x, right? In particular, what this shows is that the range of this fractional derivative operator is no longer the same as the range of the derivative operator, because the derivative operator, right, took differentiable functions on the real line, and he gave me a function on the real line, right? However, the fractional derivative operator, right, takes a differentiable function on the real line, and it seems to give me a function on the complex plane. So because of this example right here, right? So it's not clear what the range is for the fractional derivative operator. So, and that's going to be addressed in the next slides. What we're going to find out is that if we do this trick that we extend the scalars from real numbers to matrices, right? 2 by 2 matrices, then this fractional derivative operator will become well-defined. The range will be well-defined. So that's what the method will be called, extension by scalars. Hopefully that will be a motivation for other fractional derivative operators like the cube root of the derivative operator and so on. All right, thank you, and I'll see you in the next slides. Hello, welcome to the second part of this presentation. Now that we know a definition of the fractional derivatives, we're going to postulate a different definition using Clifford algebras or the algebras of matrices, right? So the previous definition attempted to define, right, the fractional derivative operator as taking as the differentiable functions in the real line onto the functions on the real line, right? However, it's a rather complicated definition, and for example, the fractional derivative of a real function, right, turns out to be complex. So it doesn't belong to the range anymore. So what is the range of the fractional derivative operator? That is to be determined, right? Because it goes beyond the real line, even though you started with something that's supposed to go into the real line. The answer goes into extension by scalars, right? Let me write this down more carefully. So what we're going to do is consider this following Clifford algebra, right? CL over R of 1 comma 1, right? That is generated by X and Y, right? They're vectors, right? Such that, well, I'll just be more precise. It's generated by the 1 plus a vector X on the plane plus another vector Y on the plane plus the wedge product of those two vectors, basically, right? So where the inner product of X and Y is equal to 0, right? No, it's equal to 1 actually. And the inner product of X and X is equal to 0, and the inner product of Y and Y is equal to 0, right? So in other words, the metric from the Clifford algebra is given by that. So in particular, we get that x squared is equal to 0, y squared is equal to 0, x, y plus y, x is equal to 1. So, okay. Right. Well, actually, take that back. I have to do this again. Well, it doesn't matter. Okay, so I got the Clifford algebra wrong, actually. So, yeah, so let's say it should really be the metric should be 1, 0, minus 1, right? So xy equals 0, xx equals 1, yy equals minus 1, right? So So this means that this should be 1 and this should be minus 1, right? And xy plus yx should be 0, right? So what we're going to do is define the A operator to be x plus y over 2 and the B operator to be x minus y over 2, right? And then the nice thing about the A and B operator are the following, right? That A squared is equal to, in this case, it's going to be equal to x squared plus xy plus yx plus y squared, right? Divided by 4. So it's going to be equal, so this part is 0, right? Equal to 1 minus 1 over 4 is equal to 0, basically. Similarly, b squared is going to be equal to 0 as well. However, there's a nice property here, right? And the property is the following. AB plus BA, right? What is that equal to? Well, let's do the calculation and then we will be set. So this will be 4, right? So it will be x squared plus xy plus yx plus y squared, right? No, actually, take it back. I'm doing this wrong, actually. Let's just do it slowly so that we're able to digest it. So it's going to be equal to x plus y, x minus y plus x minus y, x plus y divided by 4, from which we get x squared minus xy plus yx minus y squared plus x squared plus xy minus yx, right? Plus y squared, right? Oh, this will be a minus y squared divided by 4, right? So we get some cancellations, right? This one cancels with this one cancels with that one. And not only that, right? I get, which is equal to 1 minus minus 1, that's the y squared, plus 1 minus minus 1 divided by 4, which everything ends up being 1. So kaboom, right? We get the following relationship, right? So A hat, B hat, plus B hat, A hat is equal to 1. And I should be using a red marker, so because this is an important result, right? So this one and this one is also important too. So we have this Clifford algebra has two elements that are idempotent, and it has this nice relationship AB plus BA equals 1, right? Or the identity. Now let's do the definition of the fractional derivative by doing extension by scalars, right? So remember, we cannot use the functions of the real line as the range anymore, right? And there's no reason to believe that the domain of this fractional derivative operator is well defined on the differentiable functions because its image does not lie in the range of the original derivative operator, right? So we're going to have to extend the domain and the range into another space in order to make the fractional derivative well defined. And that's the plan, that's the idea behind extension by scalars, right? We're going to define the fractional derivative, in this case, the square root of the derivative operator, to be extension by scalars to the Clifford algebra, right? So Clifford algebra of 1, 1 R tensor product over R, so they're both algebras over R of the differentiable functions in R, right? And the range is going to be the same, Clifford algebra over R. So the scalars in this case are going to come from the Clifford algebra. We're extending the real scalars to scalars over the Clifford algebra. The scalars become a Clifford algebra in this case, over functions on the real line, right? Now we claim that this operator is well defined. Now that we know it, and we're going to show it, right? And as an aside, right, using bot periodicity, the Clifford algebra over the real line of 1, 1 is isomorphic to the 2 by 2 matrices over the real line. So the scalars are being extended to be 2 by 2 matrices, basically. Now we're going to define the square root operator of the derivative operator, right? So this is the definition, right? To be a tensor, the identity on this, right? Plus b, right? Tensor, the derivative operator on this, basically, right? Basically. Remember, we have a tensor product of algebras, right? The first operator acts on the first algebra, the second operator acts on the second algebra. So it's a well-defined operator, and this is over the real line, so over the real scalars. So this is this is going to be the definition. Now let's do a small calculation, right? To show that it works, right? But before we go on, right, let's consider this definition right here. There are 2 by 2 matrices, right? So A hat in this case corresponds to 0, 1, 0, and B hat corresponds to 0, 1, 0, 0, 0, right? So if you do this calculation, it satisfies all the solutions, right? So using the A and B basis, we get that, right? So let's calculate the fractional derivative of a function, right? In this case is going to be equal to A hat. So in this case, this is going to be equal to, so let's do it formally, right? The fractional derivative of the identity, right? Tensor the function, right? And then we're going to do the application, right? So this is going to be equal to A hat times 1, tensor the identity acting on the function, plus B hat acting on 1 times 1, right? In the Clifford algebra, tensor the derivative of the function, right? From which we get A tensor F plus B tensor F prime, right? In matrix notation, this is equal to 0 f of x, f prime of x, basically, right? So the derivative operator to the 1/2 of f is equal to 0 f of x, f prime of x, 0, right? Another way to look at it in matrix notation, right? So you get two possible answers. We get this one and we also get that one. Now let's go ahead and apply the operator to itself, right? So let's do square root square acting on f. That's going to be A tensor I plus B tensor derivative operator acting on A tensor F plus B tensor F prime of F, right? Let's do this one times this one, right? Then you get an A square tensor I acting on F is F, right? Plus AB tensor I acting on F prime is F prime. plus BA tensor f prime of x, tx acting on f is f prime of x, plus b square tensor derivative of f prime is f double prime, right? Well, we know that b squared is 0, right? So that cancels. We know that a squared is 0, so that cancels. Now we're left with this part right here, in which we can pull out the AB and BA, right? So this is equal to AB plus BA, right? Tensor F prime, which in this case is equal to 1 because we did that calculation in the Clifford algebra, right? Acting on F prime of X. And lo and behold, right? Remember, yeah, so I made a mistake when I wrote this down, right? So this should really be the square of the derivative upper, something went wrong. Let's do it again. So the square of the derivative operator of the square root of the fractional derivative, right? Acting on a real function which is given by 1 tensor f, right? Gives me the derivative of the real function, 1 tensor f. So we have a well-defined operator, right? It remains to show that that any function, right, that well, that acts on the range, right, on the domain, any function that acts, if I put any function in the domain, I get a function on the range. That's what it remains to show, and that's what we're going to do next, actually. So, hello again. So let's continue the calculation or the presentation of the fractional derivative, right? Remember, let us recall that the fractional derivative operator that we defined, right, is defined on the Clifford algebra, 1, 1, tensor the differentiable functions on the real line, right? The image is going to be the Clifford algebra, 1, 1, tensor the differentiable, just the functions on the real line. Okay, so having said that, right, we did the calculation for the particular. So actually, before we go on, the Clifford algebra is spanned by 1 by the A Clifford number, by the B Clifford number, and by the A wedge B Clifford number. Now, this is not an orthogonal representation. This Clifford algebra has an inner product, right? But this decomposition is just a vector space decomposition, but they're not orthogonal. Okay, so 1 in this case is going to be the identity matrix, right? 1, 0, 0, 1, right? A is going to be the 0, 0, 0, 1 matrix. B is going to be the 0, 1, 0, 0 matrix. And A tensor B is going to, A wedge B is going to be equal to the matrix 1 minus 1 half 0, basically. So, yeah, so it's interesting to see this. Of course, they're not orthogonal because these two guys are not orthogonal, but this guy is orthogonal to those two, right? But yeah, so right. So anyways, so what we did is we calculated the derivative operator on a differentiable function, right? So the differentiable function in our extension of scalar setting is going to be equal to the identity matrix tensor the function itself, right? Now, if I apply the derivative operator twice, I get the identity matrix tensor the derivative of the function itself. So in other words, the square of the fractional derivative leaves this space invariant, that is the space of functions. So if you extend a function by scalar, right, to the Clifford algebra, you're really extending, you're doing the identity tensor of that function. So it leaves it intact, right? So now let's look at the genetic definition, right? And remember, in the domain, there is I tensor F plus, in this case, it's going to be A tensor G, right, of X plus B tensor H of X, right, plus, now let's call this, now normally I will do A wedge B, right, but I guess we could do well, let's just do A wedge B actually, so see what happens times, well, no, let's not do A wedge B, we're going to do AB basically, right, which in this case is going to be 1 0 0 0 1, right? These two guys are linearly independent, right? Yes, they are linearly independent, but they're not necessarily orthogonal. So tensor, so FGH, let's call it L of X basically, right? So this is a generic term, generic term in the domain of extension by scalars, right? So let's see what happens when we apply the derivative operator to it, right? Okay. So the first one we know, right? So I guess it's just a matter of doing this, right? So this is equal to A, remember, 0, the identity here, and then the derivative over there, right? So if we calculate derivative operator A, you get 0, the identity, ddx 0, acting on 0, 1, 0, 0, from which we get 0, 0, right? Plus 0 plus the derivative here, basically. Yeah. Right, that's that operator right there. So it's going to be 0 I ddx 0, 0, 1, 0, 0, from which we get the identity over here, 0, 0, 0, 0, right? And dx 1 half AB is equal to dx 1 half AB in this case is going to be, well, let's just do it slowly so that we can get it done. Yeah, AB in this case is 1 0 0 0 0. So we get 0 ddx 0 0 0. Okay. Okay, now we got that part done. So we get the following basically. So this is equal to 0 f prime 0, right? plus, in this case, it's going to be equal to 0, 0, 0 dx acting on, in this case, it's going to be the identity gx, right? Yeah. So let's call it g of x, basically, plus the identity 0, 0, 0 h of x plus 0 d of x, 0, 0 acting on L of x. So I get 0 f prime 0 plus 0, 0, 0 g prime of x plus h of x 0, 0, 0, 0 plus 0 L prime of x 0, 0, 0. So we get the following result. The fractional derivative of a genetic term, right, is given by this matrix, basically. So h of x, f of x, right, get f prime of x plus L prime of x, and then g prime of x, basically. So that is the definition of the fractional derivative of a genetic term. It clearly belongs to a mixture of differentiable functions and functions that of a real variable, right? So they're not necessarily differentiable anymore. So yes, so does h need to be L of x? Does h need to be differentiable? Let's see. No, h does not need to be differentiable. Anyways, yeah, so that is what it is. Now let's consider what happens when we do e to the minus x, right? E to the minus x, the fractional derivative, right, is given by e to the minus x minus e to the minus x 0, right? Which is equal to, I can pull out the e to the minus x, right? And I get 0 minus 1, 1. And this is nothing more than e to the minus x minus the J matrix, right? Where J square is equal to minus the identity 2 by 2. So it's a root of unity, right? So yes. So in a way, this is equal to I basically, right? So remember the result that we had first? So it makes sense. Let's see what happens when we do the derivative of 1/2 e to the minus e to the ax, right? Then this would be 0 e to the ax, a e to the ax 0, right? So we can pull out the e to the ax and we get 0, 1, a 0, right? Right, so what is this function e to the 0, 1, a, right? 0, what happens when I multiply this matrix 0, a, 0, right? I get a on the top, right? And I get 0, 0, a times the identity, right? So this matrix, right, let's call this capital A, right? Has the property that a squared is equal to a times the identity, right? So it's otherwise known as the square root of 1/2 times the identity. So yeah. So it checks actually. Remember that this was equal to a to the 1/2 times e to the ax in the previous definition. Well, in the matrix formulation, it has a similar answer. So yeah, so okay. I hope this helps. It's an introduction to fractional derivatives by the method of a scalar extension. So we're extending the scalars from the reals to a Clifford algebra where the fractional derivative becomes well defined. Just remember that these matrices will mimic complex numbers or real numbers or just matrices in general. So question is, can you formulate the the cubic root of the fractional derivative or the quartic root of the fractional derivative? Leave that as an open problem. Hopefully someone figures it out. Thanks. Okay.